So how many of you have heard the terms artificial intelligence before coming into this room? Great. How many of you have heard the term machine learning before coming into this room? Right. So interestingly, it's a similar number. I'll talk about why the two are so closely related. So the idea why it's called approximating intelligence and not artificial intelligence is something that we will talk about more in the topic. So, right. So before I begin, there's been a lot of conversation about AI. All of these companies have divisions that just do AI research. They have products like Google Home, Apple Siri, Face ID. They're using every day. They use AI, so to say. So, who is this? What is the purpose of this talk? With all of this stuff already out there on the internet, I guess the purpose of the talk is to be able to give you the tools to understand the things that are already out there on the internet. There's a lot of information, a lot of news articles that talk about these things, but sometimes they don't talk about the fundamental ideas behind these sort of technologies. So the idea is to introduce you to these different concepts so that you can go back home and understand all the news articles that you read before. Cool. Who is this for? This is for anybody who is interested. There is no background of mathematics or computer science required. If you're interested, this is for you. Or at least that was the intention, and I hope that comes through. Right. So roadmap for the evening, there are 3 sections. The first section is going to be what is AI, what is machine learning, how are they related to each other. There will be a break after this in which you can ask questions. There is section 2, which talks about how does machine learning really work? Like, what's happening there? How is it related to AI is covered? But what does even happen when I say a machine is learning? What does it mean for a machine to learn? The third part is why is it suddenly so popular? There's been a surge over the past few years. It's all over the internet, all over the media outlets. What happened? What is the reason why it's suddenly popular? And what are examples of things that it still can't do? So just to give you an intuition for these things. Cool. So before we really begin talking about these things, let's try to take a look at one such intelligent robot. So this is from the movie WALL-E, which is one of my favorite, so to say, sci-fi movies. Right, so we begin with this to sort of set the stage, right? Because when we say we want to make something that's artificially intelligent, we want to have something in mind about what we want to make. And this is, in some sense, an embodiment of what we want to create. We want to make a robot that can actually do these things, right? So let's take a look at some of the capabilities that WALL-E must have had to be able to do what it did in this short clip. Well, it recognized the cockroach. It was able to communicate with the cockroach with gestures. It was able to walk around in the rugged terrain, which was, it wasn't like a clean, neat, uniform road. It was walking across these potholes and things like that. It was being curious. This apparently is a really hard thing to do. And I'm also sorry for the typo. But so it was being curious, and he observed many objects. He found some interesting, some of them were not interesting. He learned to operate a new object that he had never seen before, a fire extinguisher. He also sort of had a way to get back home at the end of the day. He was able to find his way back home in the new terrain. So the real question that stands out is what makes WALL-E intelligent? If I was to ask anybody, arguably we would agree that WALL-E has some notion of intelligence. But what about him really makes him intelligent? Is it one of these tasks? Is it all of them together? We need a definition because computer scientists can't work without really a definition. So we need to have a definition to be able to work. Right. So this brings us to the big question, right? What even is artificial intelligence? And I'll be very frank, this is more on the domain of more philosophy than computer science because there's multiple definitions that people believe in. But the general one that most people would agree on is that when we talk of things like Apple's Face ID being artificial intelligence or Facebook's language translation systems or Siri and things like that being intelligent, that's not exactly what we mean when we talk about intelligence. There is no real clear definition, but we have a clear goal. And the goal is to be able to make a system that has the same characteristics and can do same tasks as an intelligent being can. So you, me, we are intelligent beings, supposedly. And the idea is that a robot should be able to do the same things as we can. Right, so that's the goal, so to say. And we need to give robots the capability to do these intelligent tasks. That is, so to say, the end goal, and that's what we're working towards. Cool. So how do we do this? Like, that's the big question, right? How do we teach a robot what an intelligent task is, and how do we teach it to solve it? So let's go through a thought experiment. Let's start with a task that would be considered intelligent. You have this block of wood, and you want to make this chair from it. So I need a volunteer for this one. What do you think I need to be able to go from this block of wood to this chair? Sure.
Are you talking about tools or are you talking about
That's it. That's what I was looking for, tools. So what you need in between is a set of tools. You need a toolkit. And when you take a toolkit, you're able to take something that is unprocessed and you're able to take it to something that's more useful. That's what toolkits allow you to do. And that's exactly what machine learning does. Machine learning is the toolkit that you use for artificial intelligence research or for making a system that is artificially intelligent. You will need a toolkit. This toolkit uses mathematics. It's called machine learning. So one way to define it is to say that it is a system which takes in information and is able to transform this information into more meaningful information. I realize this is a bit abstract, so I'll give you some good examples for this. But just keep in mind this diagram, this figure of information going in and more useful information coming out of this box. Cool, so let's look at some examples to get a feel for it, right? You can take a picture of a chair. You can feed this into your machine learning system, and it can give you a label saying that this image is of a chair, yes or no. You can also pass inside this chessboard and say, I want to get from the red cross to the green cross. What do I do? How do I get there? And the system will tell you, take 3 rights and 1 down, and you'll get there. You can also say that you have this 21-year-old who speaks English and likes pop music. What kind of music would this person like? What artist would you suggest? And you'd probably suggest Ed Sheeran. So there's a high probability they might like Ed Sheeran. And all that I've done here is that I have transformed from one information to more useful information. And that's exactly what machine learning allows you to do. Cool. So the important key insight here is that intelligent tasks can often be represented as transforming from one piece of information to another. Because we will all agree that this requires some degree of intelligence to tell if this picture contains a chair or not, or to predict someone's music preferences, or to find the right route in a map. It requires some degree of intelligence. And the important insight here is that all of these tasks can be written as transforming one piece of information into another. And that's what machine learning allows us to do. Cool. So machine learning allows us to learn an approximation to transform from one piece of information to another, which is basically to say that it allows us to approximate an intelligent task. And the word approximate here is extremely important. I'm not going into the details of this, but the way it works out mathematically is that you're learning to approximate something. So we won't go into the detail, but just remember that's important. It's going to come later. Cool. So intelligent tasks, something that machine learning can help us do. And by learning this transformation between the informations, we have something which can do tasks like learning what a chair is, learning how to find your way back home, and things like that. Cool. So I call this the AI machine learning bridge because I think that the news pretty often uses these two terms interchangeably. What artificial intelligence is and what machine learning is. And the difference here is that AI is almost like a goal that you want to give, that you have a machine which has the capability of performing intelligent tasks. For each of these tasks, you can use machine learning to teach the robot this particular task. So in some sense, by putting together a lot of machine learning systems or a very advanced one, you'll be able to move towards something that is artificially intelligent. And that is why, sometimes people say they made an AI which can do something. I think the right way to phrase it is to say they made a machine learning system which can do something. Cool. But the most important question that comes up is, like, why do we even need machine learning? Can we not just tell a computer what a chair is? I mean, I think I can point to this and say it's a chair to you, right? Why can't I do that to a computer? What's so hard about it? Should be able to just point out and say, hey, that's a chair. Just next time you see it, you know it's a chair. So why can't we do that with a computer? Right? That's something that we should think about. And the answer has something to do with the way computers work very fundamentally. Computer programs are basically just a set of instructions. That's it. You give them a bunch of instructions and they follow them. They follow them much better than any human would, but that's all they can do. So you ask them to open Facebook.com, they will. You tell them to download a picture and show it, they'll do it. But that's it. The problem is, to do this, you need to teach the computer the definition for what a chair is. If you can define a chair and tell, hey, look for this definition, the computer will find it. So let's try and find a definition for it, right? Let's try and find a definition amongst each other. So I need a volunteer for this one. How would you define this chair? Does anybody have a definition for a chair? Anybody? Okay, so 4 legs is a definition that definitely works for this one. But would you say these are chairs?
Yes.
And they don't have 4 legs. And if a computer was to say that these aren't chairs, then you would say it's not intelligent. It just thinks 4 legs are chairs. So the thing is, all right, let's try for another definition, right? How about we say it's a surface that we can sit on? Well, that's pretty much me every day. I don't think that's so. The surface on which we can sit is also a thing that doesn't work, right? So the problem is that giving a very clear definition for what a chair is, or what any concept like what a cat is or what a car is really hard, and we can't give a clear definition. And this is where the approximating part comes in. When you can't define it, use mathematics to approximate it. At least that's all that we can do in computer science. So that's the idea. Defining is hard. When we can't define, we use machine learning to approximate the relationship between these two ideas. Once again, as I talked about, the relationship or the transformation is between 2 pieces of information, like an image and what is inside that image. So what I can do is that I can take this information 1, which is picture, and point at this, and I can take information 2, which is does it contain chair, yes or no. And I can take a lot of these examples and give it to my computer. And what it does is that by looking at a lot of these examples, it learns an approximate definition. That's what's happening in machine learning. It's looking at examples. It's learning an approximate definition or an approximate relationship between 2 quantities that are given, or 2 pieces of information, as they call it. This, as we'll see, is like the first part of machine learning. I'll talk about the 2 parts as I go forward. But that's the basic idea. When defining is hard, learn to approximate. Why is it called learning? What is being learned here? That's something that is worth figuring out. What's being learned here is the relationship between the 2 quantities. So when we do machine learning, when we say the word we are training a machine learning system or something like that, you might come across in the news sometimes. What's happening, what is being learned here is the relationship between the 2 pieces of information. And by giving it examples, you're helping it learn better and better. So that's one of the key, most important pieces of sort of important things about machine learning is that as you give more examples, it improves over time. And that's why we say it's learning over time. Cool, so here's the same thing example shown again. The information that goes in can be pictures, and it can start telling you, does it contain a chair or not? You can have a rough map of a city, and you can ask it, what is the best way to go back home? So things like this. Right, so the 2 steps of machine learning, right? The first stage is what we call the training or the learning step. This is where we're giving it samples and we're sort of letting the machine learn or understand what the relationship is between these two kinds of information. So it can be the picture and the label, it can be the map and the route, it can be information about people and the music preferences, and it's just learning right now. Once it's learned, then I can start testing it. So the testing and or the prediction is the second step, where you have a system which has learned what the chair is. Now you can give it a new picture, which may or may not contain a chair, and ask it, does this contain a chair? That is the testing step. So you want to be able to achieve this. That's what you need. This is once the machine learning system has learned, you can say that it is done learning now, I can use it for purposes. And that's the second step. So to be able to get here, you need to do this. This is basically section 1, where I'm just introducing the ideas that we're going to be talking about in the next sections. So artificial intelligence, to repeat it, is a system which has the same capabilities and the same characteristics as intelligent beings have. Right? Machine learning is a mathematical toolkit that we use for artificial intelligence. The reason we use it is it helps us approximate intelligent tasks which we can't give a definition for. So machine learning, when put together, can help us further move towards artificial intelligence. And that's why they're often used together. Cool. This is basically the first way. And if anybody has any questions about these things, feel free to ask.
Slide with 2 steps.
The 2 steps? Yes. Oh, sorry, moving opposite direction.
No, forward to training and testing. There we go.
This one, yeah. So these will all be available online anyway, so you can do it. Does anybody have any questions? Sure.
When the process of training learning, does these algorithm, they save information in somewhere so they can recall that thing that they learned in the past, or is it just improve the algorithm so it's more accurate the next time it needs to generate the information?
That's a very good question. So the question here was, whatever the machine learning system is, I'm going to rephrase the question so that everybody gets it. I think the question was, when you're training a machine learning system, is it learning just how to handle these pieces of information, or is it also storing something that it can reuse later? And the answer is yes and no. It's storing what is extremely important. So the way it works, as I'll talk about later on, is that it does a bunch of calculations on the things you send it. So the information goes in, it goes through a bunch of calculations, and something more important comes out. So while it does not store everything, what it does store is what kind of calculations do I need to do. So it stores some small, it takes some memory. It will store something, that's almost like learning, right? If you go to a class, you start learning something today, you will use some memory in your head. But for the most part, you won't be like memorizing it. You'll be learning something that will be better than just memorizing it. So it's not memorizing, but it is learning. So it takes some memory, yes. Does anybody? Yeah, sure.
I have a question. So in case, like as you said, once we test the data, then we train the data, then you want to predict something like, say, a sales prediction or something like that.
Yeah.
So when something like that happens, so we're using machine learning as a mathematical tool, right?
Yeah.
So we are actually creating a system. We're just using it. So is that what you're trying to say?
Could you repeat the question?
So when you test and train data and use it to predict the data.
Yeah.
So we are basically applying the machine learning mathematical toolkit as an algorithm to convert the data into more meaningful information.
Right.
So we are actually not creating any artificial intelligence system, just using the toolkit.
So what we are creating is the capability to be able to make the predictions. So it's arguable what intelligence is, as I mentioned, right? And in this case, the way we're defining intelligence is the capability to do certain tasks. So by creating the capability to do something like sales prediction or music preference prediction, I have created intelligence in some form, and that's the idea. Yeah, and as you said, it's just the algorithm which is not sort of learning over time. The idea is that it does learn. What it learns is sort of tweaks the algorithms in a certain way, and it remembers that to do chair identification, I need to use this tweaked version of the basic algorithm it's giving. And then it remembers that's how I do chair identification.
This may just be a follow-up to that.
Yeah.
So essentially, two inputs is here's a picture of a chair, or here's a picture of a chair, and this is me saying yes or no.
Yep.
And then basically you do that a billion times.
Yeah.
And it'll pick up on repeating themes, blah, 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 commonalities between the pictures.
Right.
It'll make accurate, it'll make its best guesses as to what the key elements of a chair is.
Exactly.
They're basically its own definition.
Right.
And therefore you then get the prediction phase, throw it in and see what it's quite learned is accurate.
Yes, that's pretty much it. So there were a lot of terms that I don't want to get into right now, so I won't repeat the question to everybody, but we'll come and cover all of this anyway. So it's fine. Don't feel left out if you didn't understand this part right now. Cool. Does anybody else have any questions? Sure.
As far as is there a way to train machine learning system to recognize functionality that's just vision and visual identification?
So as long as there is so the right way to say it is that the information that you throw in, if it contains what we're looking for, and you can find the right kind of mathematics in the machine learning system, it will work. So for example, what that means to say is that if I have data where I'm talking about functionality of, say, something like tools, right? So what I can have, this is a hammer, it's used for beating. Here's a knife, it's used for cutting. And if I have data set like this and I feed it inside the system, it's going to work. That doesn't even need to be a picture of a hammer. It can just be the word hammer, and it will learn that. But it's worth wondering that what will happen if you give it something like the age of a person and try to predict the gender of the person. Can any logical system do that? And the answer is no, because someone's age is not indicative of their gender. It may be very weakly indicative of their music preferences or their movie preferences, but someone's age doesn't tell me anything about their gender, right? So there's nothing there that a machine learning system can learn. So if you throw in data like this, it's going to be a garbage in, garbage out thing is what we say. You throw in garbage, you get out garbage. That's what we expect. Right?
Like Wally.
So yeah, I'm going to proceed to the next section just to sort of stick in the time. But yeah, these are some good questions, and there'll be more volunteering opportunities as well, and please keep asking questions with us. Awesome. So we saw the summary of section 1. Section 2 is, so section 1 was mostly about what is artificial intelligence, what is machine learning, how are the two related, but we still haven't talked about how the machine learning system works. How does this system learn? We talked about having this system which can look at pictures and labels and start learning how to understand the transformation between these two kinds of information, right? But how does it do it? And the answer is there's a lot of mathematics involved here, but I'm going to take out everything and just give you the intuition so that you understand what's happening. Cool. So let's imagine today you want to learn how to do woodwork. And I'm sorry for the slight typo there, but imagine that you want to do woodwork today. What are the different ways in which you can learn to do woodwork, right? You can either go to a teacher and say, hey, please teach me how to do woodwork. And in that case, the teacher will teach you how to cut wood in a certain way, how to make corners, how to round corners, and things like that. The other thing is that you can start sort of playing with the wood yourself. Buy a bunch of tools. You can start exploring with the wood yourself. And the third is you do nothing. You just sit in a room and watch catalogs of furniture and look at the different kinds of furniture that exists. And I would argue that the third one is actually giving you most information. Because by looking at furniture, you understand that chairs exist in all these wonderful ways, and beds are like this, and tables exist like this. Then all that you need to know is how to make preliminary things like, how do I make a column? How do I make a rounded edge? If you're able to figure out these things, and you have the understanding of what a chair is, you can in principle learn how to make a chair much faster. But if you learn just by example, if someone just teaches you how to make a chair, you can never make a table. You'll have to restart the whole process. So the main key ingredient here is that there's 3 ways to learn. There is by example, where a teacher teaches you. There is by exploration, where you actually tried out things yourself. And there is just observation. Right. So the ways to teach a computer or machines or machine learning also comes in 3 flavors. There is by example, which we call supervised learning, which makes sense because a teacher is supervising you. There is by exploration, which is where you're trying out things, you're seeing what looks good, and then that's like your reinforcement learning method where you're being reinforced by what you've made. If it looks good, you're reinforced to try something more like that. If it looks something really bad, then you don't want to do something like that again. And finally, there is by observation, which is that there is no supervision, no one telling you what to do. You're just sitting there observing things, and that's unsupervised learning. Right. So let's look at the 3 tasks. Like of the many tasks we listed out there, let's look at 3 tasks that we said Wally needs to do. 3 capabilities, right? There is identifying the cockroach. There was knowing how to get back home at the end of the day. And there was identifying so many objects. It was curious, but it was able to look at new things and understand what's happening with all of these objects, right? So what we're going to do now is we're going to give Wally the capability to do these 3 things. We're going to see how we can teach each of these 3 things to Wally. So we'll start with the first one, which is how do we teach Wally what a cockroach is? Before I begin, there is some terminology here. Every time I use this green box, it basically means that it's a picture that's being given to the computer. If it's 3 different colors, that means it's pictures of 3 different things. So it could be like a dog versus cat. It could be conference room versus outdoors if it's a scene. It basically means different kinds of information, right? Awesome. So teaching Wally what a cockroach is. It seems to be an important thing apparently. So it's the same as teaching it what a chair is, right? Because it doesn't really matter if it's a chair or a cockroach. It's just a picture. And if I can get enough pictures lot of pictures of cockroaches, and I can tell the machine learning system, hey, this is a cockroach, this is not a cockroach, then it will over time learn to approximate the relationship. So the information 1 that I gave it is a picture, and information 2 is, does it contain a cockroach, yes or no? And what I want it to do is to learn this transformation between these two kinds of things, right? So this is called supervised learning. It's learning from examples. Step 1, as I talked about earlier, is training or learning. So what I do is that there is pictures of cockroach. So these are all pictures of cockroaches, and there is the label yes. And the machine learning system sort of looks at these two and tries out a lot of mathematical things in between to understand what is the transformation. Then it also sees a lot of negative samples. There are pictures of dogs, there can be pictures of this classroom, it can be a lot of different things. And by looking at negative samples, it understands that these are not cockroaches. And by combining these two together, it sort of understands what a cockroach is. Because, okay, here's a good question. What happens if I never give it this, the second half one? There's no negative samples, it's all only yes samples. Well, the machine says, whatever you show me, I'm just going to say it's a cockroach. Because, at the end of the day, I'm just being given positive samples. If I just learn to say it's all a cockroach, I will always be correct. And I don't want that. Don't want the machine to do that. So I have to give it negative samples and tell it that this is not a cockroach. You also need to learn that. Cool. So this is basically the standard technique that we have been sort of exploiting for the past few years. This is whenever you read in the news that we get a lot of data, we throw it into a machine learning system, it learns something. Usually, this is what's happening. You're taking a lot of pictures, a lot of labels, and you're teaching the computer how to go from the picture to the label. Cool. Step 2, once it has learned, once it is trained, so to say, then we can use the machine learning system we trained, right? And what can we use it for? Well, we can use it to tell what's the content of a new picture. Well, we can now look at the cockroach and tell, is this a cockroach? Did I step on a cockroach or did I step on a rock? Should I be, scared I stepped on the cockroach or not? To be able to do this, there was presumably a lot of machine learning that went in before so that Wally could do this. But when it actually saw the cockroach in the video and it reacted, this is what was happening. It took a picture from its eyes, which were cameras. Nobody told it what it saw. It took the picture, this new picture. It went through its brain, or the machine learning system, so to say. And what came out was that this is a cockroach. And then it realized it stepped on a cockroach and it reacted. But this was the phase that was being activated when it realized that there's a cockroach here. Cool. Right, so training, learning, we have a picture and a label, and the machine learning system learns the transformation between these two kinds of information. Right? During the testing or the prediction state, we have a new image. We do not know the content of that, but we have a system which can tell us what is the content of that. Right, so every time you have something like Facebook tagging your image on Facebook, that's what happens. When it suggests tags to you, it's seen a lot of pictures where you've tagged yourself. So it sees that this face corresponds to this person. And now that you upload a new picture, it's able to find those faces and identify whose face it is. And that's using the testing or the predicting stage. So this is where all the money is, so to say. All the sort of awesomeness is here. And this is all the drudgery that you need to do to get here. Cool. So, right. One of the 3 capabilities is now done. We've sort of taught Wally how to not step on cockroaches. How do we teach it to get back home at the end of the day? And this, I think, is something that's getting really popular these days in the research as well. So you might, if you follow the articles very ardently, you might have read something called reinforcement learning. Is there anybody else here who has read the words reinforcement learning in this article? Hey, so there are some. Awesome. So increasingly, I believe if you read more articles, you will come across things like this. The idea here is very simple. Let's see, teaching Wally to get back home. This is Wally's world, right? It's standing at the yellow cross. It needs to get back home at the green cross. There are water puddles. Every time it's blue, it's a water puddle. And the red ones are like potholes. So imagine like this. It wants to get back home, but if it steps in a water puddle, it needs to replace its electronic parts. And that costs money. If it steps in the pothole, it has to replace its mechanical parts. And that also takes money. But if it takes a really long route, it spends fuel. And that also takes money. So what it wants to do is it wants to find a short path so that less fuel is used, but it wants to avoid the potholes and the water puddles. And obviously, it depends upon how much does it cost to replace the electronic parts and the mechanical parts, how expensive is fuel. that is what defines what the best solution in this case is. So it's not as straightforward as just like, again, defining. I can't just give a definition, because why can't I just give a definition, right? That's also an interesting question to ask. I can't give a definition because I don't know my whole world. Imagine Mars rover being sent on Mars, and you want the robot to be able to walk around, right? We don't know what potholes and things exist on Mars surface. It has to take that decision on the fly while it's walking around. So if we had everything out here, I could just write down every path. I can write down how much it cost me to get from one point to another in every possible path and pick the best one. But I don't have access to this whole world. You can see it right now because you need to sort of get a sense for it. But all that Wally can see is this part around, right? Cool. So can we use supervised learning here? We just talked about supervised learning, where we take a lot of pictures, labels, and in this case, the information will be this map, a particular path that can be information 1, and information 2 can be how much did it cost you, right? So can we get a lot of samples and just go by that? Does anyone want to volunteer an answer? Yes or no? Sure.
It seemed like you said that supervised learning, that's going to be more for things that are known or answers that are known. You can check it and there's someone or something.
Exactly.
The truth.
Right.
But it seems like reinforcement learning is when it's the unknown.
That's perfect. That's perfectly the answer. The idea is that Wally can do that. Yes, sure, but weather changes and this can keep changing. Every day Wally goes out, some pothole, there's a new pothole, or one water puddle has actually dried up, and all that Wally can see is around here. That's all it can see. So imagine Wally wants to go from here down here, right? If this water puddle here and this water puddle, both of them changed and dried up, there's a very straight answer. Just walk down that diagonal and you'll reach there. But imagine Wally's standing here and he sees that this one has actually dried up. Okay. But it doesn't know if this one's dried up or not. So there's a risk involved in going down this path. But there's also a reward. The reward is that it gets home really quickly. So it uses less fuel, but it may end up having to replace some electronic parts on the way. So it doesn't know. And it is in this uncertainty of balancing the risk and the reward is where we usually find reinforcement learning problems. Another example of this can be, imagine that this is your Pac-Man. And how many here have played Pac-Man, first of all? Right, so a lot of people have played Pac-Man, right? Imagine you want Pac-Man to sort of go from here to here and eat all the sort of things in the middle. And you can think of these blue and red ones as the bad guys, right? So you don't know all the bad guys, where all the bad guys are. If you knew that, you could just found the best solution. But that's how real life is. You want to get from home to work, you don't know where there's traffic today. So that's why reinforcement learning is getting really popular these days, because it allows you to do things with a lot of uncertainty, right? So there are other examples that you will probably, if you go and read the news, you'll probably find examples of robots trying to grab bottles. So I just picked this up right now. This also involves some degree of reinforcement learning. This can be done using reinforcement learning. So there's a lot of things that can be done using this method. But the basic idea is that the way humans handle such situations of uncertainty is that we sort of explore, take a risk, and we have a risk-reward balance thing going on. So when there's no way to get all the information, as you said, you must explore with a risk-reward setting. And when you balance that, is when you get a reinforcement learning algorithm or reinforcement learning system, right? So the way it will work is that at every step where Wally is standing, he's going to make a decision. Should I go right, left, up, or down, right? And that is going to be based on what it can see in its vicinity right now. So a good question to ask is, well, why does this even work? Why should it work? Because sure, this one can dry up, but does that mean I can make a decision based on this about something like this, about this water puddle? Well, the way it works is that probably there is something like the weather, which is why this water puddle actually dried up. So there is reason to believe that this one may have dried up, but this one might not have because it's a bigger water puddle. So there is some information about future in your present as well. And by relying on these things and by maximizing your risk and reward, you're able to get a better answer. So the way he's going to do it, he's going to start walking every day. He's going to try some risky things, probably comes back home and has to reward himself with a lot of money. Some days he's like, I'm not going to get risky. yesterday I had to repair like 6 of my parts, and then 3 days later he's like, I need to get back into the groove and like learn how to take risks and stuff. And over a period of years, it's going to realize how to manage the terrain by sort of having the right amount of risk. So that's how it learns to. That's how it learns to navigate its path, and that's how we teach sort of computers to play games like Mario or Pac-Man, or if you're from the younger generation, you would know things like Flappy Bird and things like that, right? So all of this can be cast as risk-reward balance. Every time you can do that, you have reinforcement learning. Cool. So let's look at a quick comparison between these two kinds of things. This will be quick because it's mostly recap. We talked about machine learning being a transformation between two kinds of information, right? So supervised learning, we have both pieces of information. We have information one which is like a picture, and we have a label. Reinforcement learning, there is incomplete access to information. So we can only get it at a cost. We can take a risk and get to know. When that happens, it's basically a risk-reward situation, and you do reinforcement learning. What if we had no access to information to it all? This is like an extreme case. You have a lot of pictures, imagine, but you're never told what they are. Can you do anything with it? Can anything worthwhile come out of it? If you think back to the example I talked about, the woodwork, if you want to do woodwork, you've never held a saw or a hammer in your hand. There's still something you can get by looking at a lot of catalogs of furniture. And that is what we're going to talk about now. Right? So we have a lot of pictures, but we have no labels. So what can we do? Let's look at an example. So I want someone to give me a description of what they're seeing here. Sorry? Colored squares. Could you add more to that definition? Could you add a little bit more to that? What kind of colored squares do you see? There's one more thing, which is how many of what color, right? So one way to describe this is to say that you have 3 greens, 2 reds, 1 yellow, and 1 blue, right? So that's more meaningful information than this stat, in some sense. I've organized this information to extract some meaning from it. Without ever being told what's inside it, I was able to find sort of a meaningful information out of it. And that's exactly how we will teach Wally all the objects in the world. But what we do is that, just like humans, we can do it, right? We can look at, for example, let's take a look at this picture, right? How many people here know what this is? So, but how many segways would you really have seen in your life? It wouldn't be something like thousands. It's probably like someone told you this is a segway, you looked at 1 or 2 pictures, and then you know there's a segway. So we can just look at 1 picture and we understand what the concept is. So why should computers need to look at thousands or like billions, as you said, of pictures? Can we not do it with just 1 or 2 pictures? And the key to do this is, well, the way we do it. We don't even know the answer to this, but one possible way we may be doing this is that we're able to understand much more when we look at this picture. For example, when I look at this picture, I see there's a handle here. So it's probably to hold. There's this wheel thing, so it's probably for moving around. There is this base here, so I can stand on it. And I can put all of this together and understand, I can stand on this base, hold the handle, and go around. To be able to do this, I have to have an understanding of what a wheel is, of what a handle is. And by relying on a lot of such information that I have already, by seeing patterns, I can do things much faster. And that's the idea. Let's do another experiment right now, right? So here's a grid of alphabets that I don't think anybody can recognize here because I don't know what language this is from. But try and find these alphabets in this grid. Does everybody have the answer? Yeah. Great. You did it in a fraction of a second, right? You can find these. What you did here is...
That's wrong.
Am I wrong?
Yeah, you want to put the 3rd one in on the top.
Yeah.
Yeah. So, well, apparently I can't do it. So we have generally, apart from people like me, there are others. And by and large, what we can do is that we can find objects that we don't understand, and we can say that I've seen this object before very quickly. You just saw it for the first time, and you were able to recognize it very quickly, right? We want machines to be able to do this. We want machines to have this capability to identify similar things without even understanding it. Could you take it after this section?
Sorry, is this an observation?
Yeah.
Okay, cool.
Right. So what you're doing here is what we call as something like learning by observation. And in the machine learning terms, this is basically unsupervised learning. You take a lot of pictures of multiple things, you put it into a machine learning system, and you wanted to give it something like what you did before, meaningful information, without really being told that this is a blue image, this is a yellow image, this is a green image. And it needs to do it. So once it can do this, assuming, so this is, I won't be talking about how this is done because this is probably the hardest of the three. And it's not really very much done in the technology, at least in applications these days, it's still very much in the research domain, so we skip just this much. But the idea is that if I can do this, what can I do with it? Well, if I'm just told once that this green image is a dog, I know what a dog is. Whatever new dog I see, I can identify a dog because I know how to recognize one green image from another. So imagine an alien was to come down to the earth today and it looks at our objects and it doesn't know the name for anything, right? But it looks at the world around, observes, understands that there is this one thing which is always wagging its tail. It's got 4 legs, it's got eyes, it's this cute little animal. And it doesn't know what it's called. But it overhears humans once talking about a dog. And the human is pointing to that little animal. Now he knows what a dog is. Now he can always recognize the dog. How he did it is that he was able to identify these patterns. By identifying these patterns of similarity, it was able to do what we did with a lot of samples with just one sample. And that's why identifying patterns is a very big win. So let Wally walk around the world, then identify similar objects, identify patterns, and then one fine day just sit Wally down and tell the name of every object. And if you've done this, if you can do this, in principle, you can teach Wally about every object in the world. And without all the samples that we talked about. Because it was able to observe patterns, and it needed much lesser labels or much lesser data, so to say. And that's unsupervised learning. That's why in the research fields, at least, people are talking about a lot of unsupervised learning these days. They're talking about how it's the next frontier, and we don't know how to handle it right now, but that's what everybody's sort of working on now. Cool. So, right, summary. There's 3 ways to do machine learning. One is supervised learning, which uses examples. And an example of this is what is a cockroach, what is a chair, is this picture of Obama, is this picture of you or your friend. All of those are examples which can be solved by giving a lot of examples in supervised learning. There's reinforcement learning, which is how do you get back home. You have to strike a balance between risk and reward to get the right amount of risk while maximizing the reward. That's reinforcement learning. And the third is understanding or observing patterns and using that to leverage and how to group objects without being told what really this object is. That's unsupervised learning. And pretty much most kinds of learning or machine learning research or technology that we see these days is using, at least for the moment, these 2. I would actually argue for technology it's mostly this. For research, it's recently become this. And this is still unexplored territory. Cool. This is a good time to stop for more questions. Sure.
So this is a stupid example.
Go ahead. It's fine.
There was that option, I think on Google, where you could put up a picture of yourself and it found your art twin.
Yeah.
That's supervised learning.
Yes.
How?
Well, Google has huge. So I don't particularly know about this project, but if I was to make this project, what I would do is that I would have a lot of people make data. So they will ask people to find similar images and things like that. So a lot of the times, the things that we do for Google, where they're collecting data from us, they're collecting data which can be used for things like this. So for example, there was a similar game before this one, where they would ask you to doodle, and they will tell you if this is a car or a cow. They'll ask you to actually draw something, and you draw it. So what they were doing was that they were collecting data of humans drawing certain objects, and then they could use it to make a much more robust system. So if they have something that can be used to sort of start as a game, they can put it out there, people play with it, they collect the data, and reuse it to make the system much better. But I think what you're talking about would be using supervised learning. Sure. Sorry. Sure.
Okay, so with unsupervised learning, it seems like you need to at least start at some baseline of patterns that native patterns that the system is able to scan.
Yes.
And depending on what those patterns are, it's going to determine what kinds of things the machine's going to learn. How close, at this point, say for example, can can you come to this blank slate where it's like almost starting with bare minimum elements?
Right. So what you're saying is that you still need to have some kind of knowledge before you begin with it, right?
Right.
And that's to some extent true. It really depends upon what kind of information you start with, yes. But there are ways that you can sort of go around it by using certain kinds of mathematics, which keeps it more open-ended. So the more open-ended you can keep it, the better it's going to be. But you're right in saying some kinds of primitives, so to say, would be needed. Right? So for a picture, I guess one way to think about it is the primitives you need are just edges. So I can go over this quickly. Imagine you have a picture like this. This is made up of substrokes, right? It's like made up of pen strokes, so to say. If you look at this like J looking like character, it's like there's a horizontal stroke, there's a vertical stroke, and there's this arc. So if you have these primitives, you can build this. You can think the further that this primitive is made up of like tinier lines or things like that. So you're right in saying that some kind of primitive is required, but the way it works is that it identifies these primitives automatically. You don't need to give it the primitives. It does identify them. Typically, the systems that we use these days, they do things in a chain. They will sort of do the simpler task and then build on top of it. And if you look at the simplest thing it's done, is that it identifies little patterns like edges or curves and things like that. And then it builds on top of that. One way to think that it makes sense is that if I ask you to make a cat right now on a pen and paper, how would you do it?
Sorry, can I see that again?
If I ask you to draw a cat on a piece of paper right now, how would you do it? What would be the process? So make a circle, make ears, and an ear would basically be like two lines. So you yourself would sort of like break it down into different parts, right? Machines do that as well. We don't really have complete control over how they do it. That's the whole idea. We let them figure out, but they identify primitives, yes.
Yeah, so I was looking to you for the difference. If the explanation that it's going around looking at a bunch of different stuff and identify object as being an object and observation objects, and then you go and say, oh, this is a dog.
Yep.
And then they go, great, and then it goes walking around again and you see that same thing, or whatever. They go, oh, that's a dog, because I was told it's a dog.
Yeah.
Why, in the first example, why can't you just have one picture of a chair and say, this is a chair? Like, I don't understand how it seems like it has like.
Right.
So the data set of one and the third is fine, but the first it's not.
Right. So the reason is that identifying that these two images are the same is very hard. If you could do that, then it would be solved and you could use unsupervised learning. The thing is you can't do it. So what you say is that, well, you can't identify patterns yourself, let me help you. These two things have the same pattern and this third thing has a different pattern. So you give it a lot of pictures of dogs and tell it that force yourself to think that all of these dog pictures have the same patterns. By doing that, you're sort of supervising it. It's almost like saying if it isn't doing a good job, you sort of handhold it to learn the right thing. But the hope is that it can do it automatically without you giving it too much examples. Right? One easy way to think of it is imagine you're teaching a kid and the kid isn't understanding how to add two numbers, right? So you would probably give him one example, two examples, 5, 10, so on. Depending upon how easy the kid finds this concept, which is variable for every kid and every concept, you could need something like 5 examples or 1 example. The hope is that he can do it in 1 example. The worst possibility is that you need to show him like 100 examples. Somewhere in between is like you can get away with like 2 examples. So what we're trying to hope for with unsupervised learning right now is 1 example, which is really hard.
This doesn't mean this unsupervised learning then requires some type of confirmation in it, so that one example isn't enough for identification and it knows it's.
We can talk about this later. We can talk about this in person. Yeah.
I might be able to clarify, and then you can correct me if I'm wrong. So I would answer that as it has to do with when kind of the labels are given. So for supervised learning, the labels are given during the training. You're saying like this picture is this. But for unsupervised learning, all the training has no labels. The machine learning system kind of comes up with its own categories without kind of a label attached to them, and then you come in after the training and say, this category, or this item in one of your categories is X, and then it can apply those labels.
Mm-hmm.
Is that,
That's correct.
Yeah.
Okay. Just like an option thing.
Yeah, like the machine learning thing already has its whole sort of category system set up, and then you come in afterwards and kind of give it the words for it. Yeah.
Right.
So looking at this example, the reason that I'll do that we already have 300
Right.
and we know what kinds of things are relevant.
Right.
If you had shown 2 pictures of ants, 2 different features would have been relevant, deciding, okay, that's the same thing, not the same. So that's like a sub, and we'd be looking at it, huge unsupervised learning task.
Right.
You've already decided, okay, it's all going to be in one domain and show pictures.
Right.
And they're all going to be plants. We're not going to throw in, okay, these are letters, right?
Right.
Otherwise, the system is going to mismatch.
Right. So you can go ahead, sir.
So yes, so I mean, there's something prior, which I think goes back to the first thing. Was
Yes.
You eat the notion of, with respect to a particular task, certain features are going to be relevant, and you partition the data so that that's true.
Mm-hmm.
And that's happened still sort of outside of the system. There's a magic part, it seems.
So conventionally, the way these tasks were handled was, as you said, starting with some priors, prior or some basis to begin with, right? So this has been taken from a paper where that's exactly what they do. They start with the prior of something called substrokes. So this would count as a stroke, and the substroke would be something even below. That was the conventional method. It was slow, and it required you to really sit down and think about what really makes this letter a letter versus a cat versus a car. You would think hard about it and come up with a basic structure that you could build on top of. And that was really hard. I will talk about more of this later, but in fact, this is almost a foreshadowing at this point. It's great. But this is the reason why what I'm going to talk about right now after this is why we move towards something called deep learning, which I'll cover right after this. But you're right in saying that some primitives help. The whole idea was, can we find these primitives automatically? And the way to do it is to try a lot of things, and something will work. Really, that's what is done. Try a lot of things intelligently, and one of them will work. And that's to say, break this down into different kinds of pieces. One of those pieces will be a good set of primitives to build up. And that's exactly what deep learning does in some sense.
My question is more into deep learning.
Cool.
Yeah. How hard is the first option to machine learning? When you put like a pictures and you say it's a program. I remember that some few months ago, Microsoft released a bot, and people was talking with the bot, and then the bot become racist.
Yeah.
Like it was being learning something wrong.
Yeah.
But they had to shut down the bot instead of relearn back that was not correct.
Right.
So my question is, when it learns something, it cannot correct itself. The machine learning is not made that way, or
it can correct itself. In that case, it was almost like it got out of hands. So they had to take it down, because if they've spent time trying to correct it and had got them even more worse PR, it would have been a problem. So that's more to do with companies than the technology itself. But yes, it's great that you know it, because one of the examples is going to follow up on what we just talked about, the bot at Microsoft. Cool. So I'm going to head to the next section, but if anybody has any questions, please feel free to come.
Let's take a short break.
Oh, that's great.
Yeah.
Anybody has any questions, feel free to come to me.
Yeah, we'll take about 10-ish minutes, grab some food, go to the bathroom, whatever. Come ask your question up at the front, and then we'll start with the last section. Thank you.
Hey, so hi. It does seem, well, first of all, I was surprised to hear you say that unsupervised application cutting edge, not really used, because certainly there are certain there's a lot of mathematics that's been developed around classifying images.
Question?
Clustering, all those multi-dimensional clustering.
So when I was saying that, I think it was more in terms of like there's been like 3 waves of it started in like the 50s, which is when marketing I'm assuming you have some background in the the first wave had people working pretty less samples, right? And then we had the second wave, and now so right now, because supervised learning is everything else that is unsupervised. Right now, for the products that we shipped to people sitting in Google Home, there is very little unsupervised learning. But there is obviously a lot of literature that is already like that. The whole idea is can we now, given the new technologies we have, sort of leverage all that and bring it to the new products.
So the second question sort of related to that is it does seem that iteration
a bunch of pictures of like that
might work very well. For instance, if you have some classification system that you apply,
I would guess that we could do some unsupervised learning on that, but
come up with the results that gives feedback. So at that point, you can say that well, you know, I did well with this, but
it doesn't
try
really
something a little bit different, see if you can do better, which would be
more like
that is completely true. That's like people do mix and match them all the time. For example, you have to use something called supervised plus unsupervised. They're connecting supervised learning. Then they have a system where you have something like you can have imagine I want to pick up objects. Now it has to understand if it's a picture before it starts. So it can use supervised classification to create some work the way you would work with it. That's the first step. And then you use reinforcement. So yes, you perfectly corrected saying that it is
Okay.
There are different modules that you have on
Have you seen that in YouTube where Mario Bros?
I've seen one of the ones
They teach Mario Bros how to. They say get more score for the right goals. And that's what which language program is like a list, but I don't remember which is like
I think this was I don't know the language because language
I know that
so it's like even when we work with each other we can talk about the language but guidance
and I think sure the way they bring that like
I think there's one very popular something called
setups and things that it could include.
So that's like an alternate also use reinforcement. That's what I really So
I think it's also
a matter of
like
there's different ways to
sometimes it's like blended, like maybe string two things together.
And the other question is,
yeah,
you are talking about pictures, you know, but what
those
about
are good
you teach to something what is and example, I will give an example. I was had this idea to make something for and the Legos, and there is some cameras you can the pixel, you can put like colors and give you coordinates. And I was thinking that's really nice to make some kind of thing that recognize the Legos based on a camera. It can recognize the distance of the shape of the Legos based. And instead of showing pictures, but is that also something that
this is something that can be done with things like these. So all of this is in the domain of things you could try. It may work, it may not work depending on multiple factors. So, but yeah, it's in the domain of things someone could try.
Well, just one quick comment. You said your motivating example for this was the working thing. I think you applied stuff really well. So if you think about like people being taught by sort of the apprentice method versus sort of exploring yourself versus just looking at a catalog. It's certainly the case that in terms of doing woodworking, the person who's taught is going to do it, right? Then a person who's just watching. I understand it in terms of like motivating sort of.
Oh, like that.
Yeah.
So that's questionable as well. I mean, if you think about like Ayn Rand's philosophy, right? You go back to, I don't know if you read this article.
I unfortunately did.
So the idea there is that our drop is a person who's like, I'm not going to listen to anything that they teach me. I'm going to build my own things. So the idea is that it's obviously supervised learning is much to the point. It gets the job done, right? But unsupervised learning can do newer things. So they're not competing with each other. They're helping each other.
It depends on the task. Also, these things also split out sort of like categorization tasks versus category creation tasks versus performance tasks, right? It's all sorts of different things. If you're creating furniture, obviously there's got to be sort of a performance aspect in your learning, right?
Right.
You can't be just looking at a catalog.
Yeah, you obviously have to do that. I'm not questioning. I'm just saying that a lot of the work can be done by observation, so that it helps you. Other things that it makes you faster when you learn from teacher. So if you go to the teacher, already learned some after seeing some patterns. So for example, practice speaking example. What I said was, your teacher teaches you and you know how to make a chair, but you know nothing about how to make a table. But if you already thought, if you already knew this is a chair, this is a table, and when your teacher is teaching you how to make a straight edge, how to make flat surface, and you're learning to make a chair.
These very fundamental features.
Yeah, and you can automatically keep a teacher how to make a table because you already thought of those patterns.
So that's all. I think it's really just limited in terms of observation, not looking at catalogs, but looking at people creating chairs.
Oh yeah, that's
I think the icons, was that the base? Yeah, I think I read that.
Yeah.
Very good. All right, looking forward to your part 4.
Do all these different things. You can climb over rocks, or you can answer questions about.
Oh, it seems like a lot of people are just doing neural networks, applied to specific narrative domains.
There are a lot of ways of having generalized systems. And there's a guy in my lab. Kind of he's working on stitching together multiple especially machine learning networks and have them be trained somewhat together, and then the second half is trained for a specific task and using it as a way to model the brain, where we know that things like speech comprehension and knowing what genre a piece of music is, they have some shared parts, your ear makes the sound, it goes to the same part of the brain, but then there's very different things kind of need to know or understand to make those decisions. So trying to kind of make these systems more biologically correct. But as a neuroscientist, that's my bias. Is that it's interesting in real brain, where it's a lot of people learn something interesting thing to learn about information. So I'm biased.
10 Miles lecture is all about how what you're doing is actually necessary in order for us to eventually, or no, I'm sorry, the other way around. What they're doing is necessary to provide neuroscientists with a little bit of clues as to what that should look for.
Because the one thing about so it's unsupervised learning, you show a bunch of images or whatever, the categories and groupings that the system comes up with don't have to be easily labeled by us. It's not like it'll definitely come out with exactly what you would have come up with. So if you can feed it on this data and get out
that's
description of it, then maybe that's what you look for things.
That's interesting.
It's definitely two ways being neuroscientists and big data people.
I mean, the ultimate question is what fundamentally is so different about the way brains acting like a neural network and the way that computers are implementing neural networks and so on. And because one thing is totally different. So there's some fundamental limitations to what neural networks can do as they're doing now.
Or even new, or maybe they can do build one day to do it.
No, it is not.
This is like literally our.
Hey, what's up? Hi, I'm Mariah.
Ishan.
Ishan, nice to meet you. Jenny is
Or if it's about brain.
Yeah, this
We could train a neural network.
Okay, cool. This is so chill.
Back and forth. Computer.
Oh, okay.
It was, there was no.
Yeah, well, I mean, that's why I allowed it.
No, it's exactly, yeah. Well,
But I've never been in this building.
Yes.
So we didn't do that. Yeah.
Start
Yeah,
camera.
no, it's cool. That was fun. Actually, I have to go outside. What? She had to go outside.
Okay, guys, so Spandan's going to start again and wrap us up with his last section. So I'll take it away.
Cool. So we've been through 2 sections. We've talked about what is artificial intelligence. We've talked about what machine learning is and how machine learning helps us move towards artificial intelligence. Right? We also talked about how machine learning is really done, and there's 3 different ways in which we can teach machines. But one thing that remains to be talked about is why is AI so popular suddenly? What happened that made it so popular? Was there a big technological change? Was it just that people just suddenly discovered it? There has to be something, right? So the answer is yes and no. There was a technological challenge which was solved. There was a technological challenge in machine learning. The ideas for solving it have been around since the 90s or 80s. The problem was we didn't really have strong enough computers to implement those ideas. Those ideas rely on a lot of calculations, and the computers we had back then weren't strong enough. So once the computers got strong enough, and there were some missing parts that were formed, once that was done, we were set up to sort of start doing things at scale. So what was the problem with machine learning that needed addressing? Right? And the idea is that systems learn with experience. We talked about this, that machine learning learns from samples, and as you give it more and more, it gets better and better. Just like any other student, it's important to give the right amount of information and the right kind of information. So we've had this example where we talked about if you give a machine or even a person someone's age and ask them to guess their gender, they can't do it because that's not the right kind of information. There's also the thing that if I was to give you, say when you're just like 10 years old and you're supposed to learn addition, if I give you a book on calculus, technically calculus books contain how to do addition, but it's really hard. You will probably just get lost in all that information. So it's important to give the right kind and the right amount of information. Can someone tell me what this is? Any clue? Any guesses? Close, but this is not really a picture, right? This is numbers. Yeah, it's nothing. It's nothing sense. It's just a bit of numbers. The way I made it is that I made this big table. I wrote some numbers. I got lazy, started copy pasting. So it's nothing. But that's how a computer sees something so beautiful. Something as beautiful as this picture. If you zoom in on this tiny region of the picture, the way the computer sees it is this grid of numbers. That is how information is stored inside computers, because computers store everything as numbers, right? So computers see pictures as a very large grid of numbers, and that is enough information to completely confuse the computer. So a picture is too complicated information for a machine learning system to learn from. We need to find the right subset, and the question obviously is what is the right subset even mean, right? And that's actually a very hard question. So the right subset of information from the grid of values you talked about, let's just call that the right representation for the grid, because you're taking all that lot of information and you're representing it as something similar. So what you need is a right representation, the right amount of information for your machine learning system to learn from. And so here's an example. So we talked about the chair picture going into the machine learning system and it learning that it's a chair, right? What I've added is this. The true solution is that you take this picture, you pick the right subset of information or the right representation, and that goes into the system, and then the system can learn that this is a chair. Finding this is extremely hard. So scientists would spend like many years trying to solve one problem. So for example, to be able to tell, is this face of a certain person versus someone else? Scientists spent years trying to find the right representation or the right subset of information. The same for scenes. In fact, there are 2 professors at MIT who some of the most popular work they've done has been trying to find, arguably, some of the most popular work they've done, has been to identify what is the right subset of information for recognizing a scene. To be able to tell that this is a picture of a conference room versus it's an outdoor scene, what information do I give to the machine learning system? Understanding this. So it's extremely hard, and we needed to do this for every single problem. And that was hard. It took time. It sort of cut down our capability to work on similar problems, even though they seem very similar to us as humans. It was not the same for computers. Right. So the right representation depends completely on the intelligent task behind the solve. If it is understanding what a chair is it understanding what a face is, things like that. Deciding what's right took scientists years, and every such similar task has a different right information subset or right representation. This is where deep learning comes in. Deep learning is a specific kind of kind of machine learning tool. You can think of it as like a hammer inside the machine learning tool, right? And this hammer, we knew of this hammer; it was existing. It's just that we didn't have the computers to actually implement these ideas. They've been around for quite some time. It was only recently in 2012 when one missing piece was also solved, and computers are strong enough now, and people sort of just got on the bandwagon, and everybody's now pushing on the deep learning bandwagon. So how many people here have actually heard about deep learning or sort of seen it in the news? That's a much higher fraction than I assumed, so we can talk about how popular it is in the news. It's super popular. If you think about it, there's a lot of other fields like biology, physics, in which much greater advancements arguably have happened, and people wouldn't have heard the names because it hasn't gotten as much traction as deep learning has. Deep learning is a great tool, but it's important to understand the difference between the three. So artificial intelligence, as we talked about, is the goal, so to say, of having a machine which has the same characteristics and can do the same tasks as an intelligent being can. Machine learning is a toolkit which allows us to learn approximately how to do one such intelligent task. Deep learning is a specific kind of machine learning tool, and what that is really good at is solving the problem we just talked about. Deep learning finds the right representation automatically. So the thing that was taking scientists years to find the right representation or the right information subset, that's what deep learning does. It intelligently tries out a bunch of mathematical operations on an image. So we just talked about how an image or a picture is a grid of values, right? So because it's a grid of values, you can do mathematical operations. And it tries out a lot of operations and identifies what's the right kind of operations to do. So these techniques have been around for quite some time, and we needed strong computers. So what happens in this process is that you take that big grid of values, it goes through a lot of calculations which sort of simplify. And what the deep learning system knows, or sort of learns over time, is what's the right simplification of this data set? What's the right information subset? What's the right representation? It's just three ways of saying the same thing. You may come across all three of these in the news if you read about it, but that's the idea. So how does deep learning do this? How does it like magically figure out, what's the right subset? It seems like a pretty hard thing to do. It was taking scientists years to do. It seems funny that something can just automatically solve it in no time. What it's doing is something like Lego blocks. So if you look at this thing or this thing, you don't see Lego blocks. What you see is something much more complicated. You see the scene. You see a character, you see a gate, you see this house-like thing. There's a scanning thing going on. And at the heart of it, it's all very simple blocks. They're being put together and they look like something complicated. So the big idea here is that you can take very simple things, put them together in the right order. And what you can have something is an approximation of something very complicated. In some ways, that's how a lot of people draw circles. They'll draw an arc, and then they'll sort of draw another arc. They'll draw another arc, and it starts looking like a circle. At least that's how I draw it. Really bad at it. So yeah, put lots of simple things together correctly or in the right order to get something that is much more complicated. That's the idea. So what you have here, what you want is you have a picture of a chair, and you want to get the right information from the grid of values, so to say. And the question is, what goes in between? What goes in between is a lot of complicated calculations, and it's hard to know what those calculations are. So what we do is that we sort of approximate this complicated set of calculations by putting small, simple calculations in the right order. If you've ever heard of something called a neural network, this is all that it's trying to do. It's trying to approximate very complicated calculations by putting together very simple calculations in the right or the correct order. The way it works is that it sort of tries a lot of calculations, a lot of combinations of these little steps. That's when we say it's learning, so to say. What it's learning is it's trying out different combinations. It does so in an intelligent manner. It knows what combination to try next based on how well it is doing. And on the basis of that, it sort of keeps improving. It tries something, it sees, oh, this worked out well, I should do more of this. It tries something and it doesn't work out well and it says, I shouldn't do this doesn't seem to be working. By just trying out a lot of things and this basic idea, it's able to identify what combination of simple calculations is the best to approximate a complicated calculation. That's all that neural network does. It takes, for the most part, it takes this image, puts it through a lot of calculations, gets the right representation out. From here, we know what to do. We can throw it inside a machine learning system, and it can tell us that it's there. So it was this part that was the big hurdle that needed solving. And with a lot of advancements in the research and a lot of advancements in the power of computing, we now have the tools to be able to do this. And this is all that a neural network or a deep learning system that you might have heard about tries to do. It tries to find the right combination of simple things which, when put together, can approximate complicated things. So that's basically the end of what section 3 is. Machine learning systems, just like students, need to be given the right amount and the right kind of information. Scientists would spend years trying to find it. Deep learning tries to do it quickly by approximating and trying to find the right subset. Cool. So now I think the most, I would say, the cool part of the conversation, which brings us back to Microsoft bot, right? So the bot that we just talked about, Microsoft had put out this bot where they would have something which would tweet or sort of retweet and try to get maximum retweets. And quickly it turned to be slightly racist apparently, and so they shut it down. Well, now working on the same bot, I'm actually going to be joining the same group that made that bot this summer and be working on this bot called the line back bot. What this does is you give it one line and it tries to make a rhyme out of it. So for example, if I say you are slowly becoming intelligent with the bot, it takes a Katy Perry line from a song, puts it in mind, and makes this, which is somewhat funny, I would say. And if you want to play with this bot, it's actually pretty chill. I can give you the link or something. You can just search for line back bot on Google, and if you want to play with this, feel free. But the idea here is, would we call this intelligent? Is this bot intelligent? It takes a line from you, it converts it into a rhyme. Seems like a hard thing to do. Would definitely require some degree of intelligence, right? So how many people here think it's intelligent? Just one, two. Why do you not think this is intelligent? Do you think it's a very easy thing, or do you think it's just mathematics that's not intelligent? What's your intuition for thinking it's not intelligent? Anyone? Volunteers? Sure.
Well, I mean, if we go off of what you said in the rest of your presentation, it's that, I mean, it's approximating. It's like, it's I just lost the word, so I guess I'm approximating intelligence as well. But if you look at this, okay, so it can do this one thing. But if you said, well, what do you, what does that convey as far as your feeling about how the public might see you, Katy Perry and Spandan Madan? I don't know that it would be able to say.
Right. So it's very narrow. Like that's one of the problems that everybody would have with it, right? It seems to be doing this one task very well, but this is all that it can do. We talked about this capability of doing all the tasks that humans can do, and all those things. So it seems to be very narrow in its capabilities, and that's actually one of the ways a lot of people look at this. So this is something that's more opinion than set in stone or like concrete ideas. But the way a lot of people define this is that Facebook has these things which does tagging, Tesla has automatic cars, Google has Google Homes, Apple has Siri, and they all call it to use AI to do something. And questionably, it's correct or wrong, but we would want something that's more broad spectrum, right? So if we say something like this, as compared to the bot, if we think of Siri or Google Home, which can answer much more diverse questions, we are more inclined to believe that it's intelligent. And that is something that changes with the capability of how many capable things it can do. Some may have a problem with how it works. Even if it's able to do the same task, does it work the way a human does? And that's something that some people may want before they want to call something intelligent. So when we start thinking of these things, we start moving towards something that people recently have started calling artificial general intelligence, or AGI. And the idea there is to go beyond just narrow tasks and more towards a general capability set of things that humans can do and doing it the way humans can do. Or if you want to do something like make an intelligent robot that can walk the terrain like a dog, then you want it to behave the same way a dog would. Even that would be intelligent in its own way. But that is treading more towards something we call artificial general intelligence. And if we think about, are we getting there? Are these tools like self-driving cars, Facebook, what we have, is it there already? Well, we're not quite there. We're actually not very close to it. It's still very much in its infancy in some sense. So true intelligence, if we were to define it the way we just did, it's not around the corner, so to say. Progress is being made very fast, but we're still not there. So, for example, these are state-of-the-art systems that can take a picture and tell you what's happening inside this picture. So, if you look at this one's my favorite. An airplane is parked on the tarmac at the airport. Right. So, there's multiple reasons why this may happen. One obvious reason is that it's always seen airports that are parked whenever there is a road. Otherwise, there is no reason for a picture to have a plane and a road together. And what's happening here is that it has no notion of what's really happening here beyond the objects, like there is a plane, there is a road, and the usual relationship between them. The usual relationship is that a plane is usually parked on the ground in all the data set that you would give it. So the flaw here is not that it's not just seen it before. So, if you give it a lot of samples like this, it'll probably be able to understand. Yes, but really that's not how we work. We don't really need 15,000 examples of a flood to know what a flood is. We understand this because we have some notion of why is this happening the way it's happening. This seems odd. How could this happen? Such reasoning processes, such understanding of what has led to this, some causality behind what is happening here is something that these machines don't have right now. And it's essential to have these things to be able to say that this machine is intelligent. So, for example, when I was growing up as a kid, I would be given this image and I'd be asked to write an essay about it. And every student in the class would come up with a completely different essay, which would be extrapolating it in ways just completely new. So, to be able to do these things, you need to think far beyond and far behind about what could have led to it, where can this lead to, things like that. And machines that we have right now aren't capable. They are task specific. And even at that task, they sometimes fail because they don't have these capabilities. So progress is fast. There is a lot left to do, but we have such videos coming out pretty often, which are scary, I guess, sometimes. So this one's Boston Dynamics robots helping each other open doors, and we can scan it as right around the corner. So he looks for a friend. The friend opens the door. Once again, think about how complicated this must have been. The robots have to communicate. We don't know what language they will communicate with each other in. How will one gesture to the other? That one realizes I need to help this other one out. There have been sort of these results in psychology where they show that a young kid is able to understand that someone's looking for help them out. It's actually a very nice video. I didn't have time to include it, but they've shown that very young kids have this ability to understand body language and help out each other. Robots, can they do it yet? I don't think that's how it worked out. There's probably something more direct about, can you help me out, by just telling the signal. So the signal just says to the other robot to come and open the door. That's all. It's not like one realized by looking at the other and have empathy to say that I should come and open the door and things like that. Right? At some level, all of us understand that this is not happening, but it's good to have it at the back of the mind because a lot of times, things get sort of sensationalized in the media, and it's easy to sort of lose track of what's obvious. Right. So ever if you get confused about what's happening, and really what's the success of how far we are right now, just remember this video. It's the same.
Now everything doesn't go exactly the way it's supposed to.
Right, so this is a video not from the past. These two have been released in relatively the same time frame by the same company. This one is actually their flagship product. The other one is new. So there is still a lot left to do. And so it sort of brings us to the last thing I want to leave you with, which is how do you make sense of the news that you read today? Because that's what I started with, right? I want to equip you with the tools to be able to understand the news that you read. Every time you see the phrase or hear the phrase, Google built an AI that does X, Y, Z, reread it in your mind as Google made a machine learning system that does whatever it does. That's more accurate, and that sort of keeps your thoughts on the right track. If you read a news article that surprises you, like, oh, did this really happen or something of that sort, just take a moment to read the original source. It takes time, but it's worth it given sometimes that news can be all over the place. Media can sometimes sensationalize, but I think now we are equipped to make sense of it without being biased. We have the tools to understand these things and understand where they're coming from when they're writing a news article. Which brings us to our final summary. So AI, as we talked about, is a set of rules, which is to be able to make a machine or a system which can do the same kinds of things as intelligent beings can do and has the same characteristics as intelligent beings do. That requires, among many other things, understanding what a chair is. So AI needs understanding chairs. To do so, we need to give an exact definition because computers follow programs. If we can't give a definition, we can't write a program for it. But we realize it's very hard to give a definition for a chair. Because we can't do that, we rely on machine learning to approximate this task or this definition. So machine learning approximately learns how to do this intelligent task. How does it do it? It does it in 3 ways. Either by learning examples, either by learning from examples, by exploration, or by observation. These are the 3 kinds of learnings that we talked about. Okay? This requires giving the right amount of information, as we talked about, or the right representation. Deep learning automatically finds that representation, and that is why it's been this it's been at the center stage of all the AI developments that have been happening in the past few years. So it's a major success for AI. But we're still far from true AI. This is, again, opinion, and please take it with a pinch of salt. News may sensationalize it, but as I said, now you have the tools to be able to understand it for yourself without any bias. That's it. Thank you.
Yeah, we can take some more
Any
questions. Yeah,
sure. Yeah.
So you showed the 3 images of the airplane and then the flood.
Yes.
And you said, we as intelligent beings can see this flood image and know it's not just 2 people, on a beach day. But that comes from a lifetime of experience and knowing what things are good, what things are bad, and when people are happy, when they're sad. You might not expect a child to be able to identify the same patterns as adults can. And so is it kind of like a parallel to how you guys think about AI that, is it fair to assume that a computer that's has as much information as a child can make the same observation as an adult?
So multiple things you said there. One, in terms of the amount of information that a child has, people who believe in deep learning and in the form it is that we have today, actually say that kids have so much information. By the time they're 3, they see so much that to be able to have a computer that can do the same things, you just need to give it more information. And the problem is that you're not giving it information. There's the other camp, which I sort of belong to as well. And we believe that you need to have more than just pictures or more than just what we give to this computer. What you need to have is some idea of prior experiences, as you just pointed out, right? So prior experiences can come in different ways. It may come from, so what kind of prior experience is needed is also very hard to figure out. And how do you incorporate it? But it is true to say, some people believe that some prior experience can be very helpful as opposed to having a lot of pictures. The prior experience of observation can help you identify objects very quickly. Similarly, some idea of prior experience of people on the beach, if they're looking in distress, so that is understanding emotion of people, that kind of so emotional understanding kind of experience can help understand that image better, right? So it comes down to what kind of prior experience you want to incorporate. But yes, that is one way to do it, and there is another way which is not using. Sure. Sorry.
Yeah, I just wanted to actually follow on to the response when you were asking about the line backlog.
Yeah.
So I think the summary here was very well put, but in terms of like, I think the specific example,
yeah.
There's also a little bit of ambiguity because there's a difference between consciousness and intelligence. So with the AGI thing, I'm just completely curious your personal opinion.
Yeah.
As or if we get closer to AGI, do you think there's a risk of getting closer to consciousness? And then, are we creating this slave race for us and not really paying attention? What do you think? Like, do you think of that as a risk, or what is your thought on that in general?
To be frank, this thought has come to my mind, but I really do believe there is so much in the future that I'm not thinking about. Really, that's not the answer.
Even with the second season of Westworld.
or that moment, for that matter. I think yes. I think it's there's a lot for machines to learn. There's so much that needs to be done, especially in terms of going beyond the tiny specific applications we talk about. Even moving from one to another is really hard. It takes not just so. When I said deep learning automatically does this, what that means is that there are 10 graduate students spending 6 years trying to solve one problem, and 10 is a small number. Trust me, for things like understanding faces of people and things like that, you would have thousands of graduate students doing it. So it's not straightforward how that can be done either. And even if it's not even straightforward, if it can be really done well, it's enough. So I think it's far enough in the future that it's okay.
Okay, you talked about computers, becoming powerful enough to implement machine learning recently. Now, is this, primarily still von Neumann type machines, that are follow a list of mathematical instructions, or is it any of this inspiring new hardware architectures that totally think outside the box of performing computing?
I think the answer would depend on the definition of the question. Yeah, sorry. The question was. Technologies have changed over the time, but how much has it changed? Is it inspiring some new kinds of infrastructure in computers, or is it still the same kinds of machines that used to be back in, say, 60s or 70s? Right? I think the answer depends upon the definition of the word new. There have been advancements, yes. If I was to talk about the von Neumann architecture, first of all, it's not something that I know very much about, but I would say that it's not fundamentally changed. What we're able to do now is that we're able to do calculations in parallel as opposed to just, but that's also been for quite some time. So yes and no. Mostly it's just machines becoming smaller and more powerful. The infrastructure, the base not changing, but I'm not the best person to answer that question. So.
Actually, they've made new chips and there is new hardware which is optimized just for neural networks or other. I mean, Qualcomm has
TPUs. Anyway, that's a point for later talk.
Yeah, there are.
Yeah, sure.
In your experience, I remember that some months ago, I don't remember if Google or Facebook, they made those two bots and they asked them to communicate, but they were explicitly saying, whatever you do to communicate, you cannot invent a new language or something like that.
Right.
And these bots, they override that instruction and they start to talk with each other. So the engineers, they didn't know what they were talking about. And they were thinking about dangerous and they shut down but they override this instruction.
Categorically for this, I was actually going to add this to the talk I did for some reason. But this example is completely wrong. It did not happen. It is the classic example of media will blow out things. Please don't take it into account. So what happened was that the person who worked on this project, his name is Dhruv Batra, in case you want to Google about it. He works with Facebook, and they were gone for a conference. They'd gone for a conference for 4 days, and when they came back later, they realized that things had just gone out of control. There were the thousands of mails, news everywhere which talked about people, Facebook's bots inventing language. Could not have happened just because it takes so much to even understand what a language itself is. There are so many structures that it requires to create a language. If these systems are never informed about that, if they're never told that to make a language, you need to have these components, or at least if it's not optimized to create a language, it can't create it as a byproduct because it's just not powerful enough. Computers can't override instructions. They just can't. That is fundamentally how computers are made. If they override any instructions, there was a flaw in the instructions. That could have happened because humans write instructions. But computers fundamentally cannot disobey at this point. If you give them confusing sort of instructions and they distort it somehow, then it was to be blamed. But yes, I think it almost connects back to, like, if there's any enthusiasts of like robotics conventionally, Asimov is someone who wrote 3 laws of robotics and things like that, right? So if you make computers build on those and they are able to find a flaw in that which optimizes something you ask them to optimize, then they may go out. But it's all going to be on the hands of someone who coded the machine. Can they go out of control in a way we don't understand? Yes, completely. Because the machines we just talked about, the important information that it's trying to understand and things like that, we don't really understand what a computer understood. When we talk about the right representation, we don't know what a computer understood. It did something which works well. So is there a danger of us giving it instructions which lead to an outcome we didn't think about? Yes. Can a computer override instructions? No. Any questions? Sure.
So, in the statement, IBM says that in by 2025, computing power in the world will be a mice brain, and by 2045, could be at par with human brain.
Right.
So my question is, a lot of people like Elon Musk, who's doing neural link, so working on human that. Right. So, do we really need to supervise the growth rate of the AI?
I would say it makes sense to me. Once again, I'm not at all an expert on the ethics of AI or how it's going to develop as a field. I think that there is a lot of conversation about this from people I respect a lot, like faculty members who've been in the field for the longest. They advise that it's required. I think even the biggest enthusiasts of AI, like people like Andrew Ng, if anybody's like heard the name of the news, he's a professor from Stanford, who's one of the sort of forefathers of modern AI research. Even I'm sure he would also agree that some degree of like regulation is required because people have these incredible tools. So regulation being required, I think it's obvious for every tool which is powerful, some regulation is required. But in the sense that's like talked about by Elon Musk versus Mark Zuckerberg, I think I'm not the best person to talk about it.
So I answered the question. So
yeah,
my question was, I know you put AlphaGo. So
yeah.
Is it a unsupervised learning or is it like a reinforcement learning?
It's all over the place in terms of mixed. So it starts with the original. So just to give everybody context, the question was: is AlphaGo the thing that Google's DeepMind made to play Go? Is it supervised, unsupervised reinforcement learning? How does it work? And the answer is that it's a monster. It's a big monster which took incredible amount of engineering and research thought. But it's a great field. It's a big achievement. And the way it works is that the original iteration of what was made was called AlphaGo. The second new one is called AlphaGo 0. So AlphaGo started with some supervision, where it started with some ideas of how to play the game. Some experts telling what things are good, what strategies are good and not. And from there, it made its own strategies. AlphaGo 0 started from scratch. So it's been never given any input data. But there's a lot of reinforcement learning happening in both of them. So if I was to give one particular answer to this question, the answer would be it relies on reinforcement learning. That's the bulk of it. It plays itself. So the thing is that Wally walking around on the earth, it takes time for Wally to walk. It takes fuel and stuff. To play a game, just keep playing the game if you have the compute power, right? So that's the answer.
The process of deep learning, in order to find the correct combination of simple equations, approximating a complex one.
Yes.
That's what you call the neural network.
Yes.
Is that is that the exclusive function of deep learning? And what I'm sorry, is doing that to find the appropriate representation of data? Is that the exclusive function of deep learning? And regardless of that, is deep learning applicable to across the three various types of learning?
I would say that it's not an exclusive function. It's a very primary function. It's what
Can you repeat the
question? The question was, sorry.
That's great.
The question was deep learning. I mentioned that it's used very often to learn the right representation of the data being given. Is that the exclusive function, or is it can be used across multiple domains and things like that? That's what the question was, right?
And then is deep learning applied across the supervised, unsupervised, and reinforcement?
Yes. Yeah, so deep learning is used across the board on all three kinds of learning. Yes, I wouldn't say the primary function is to learn the representation, but a very big important chunk of the function is to learn the representation. Yes, the right way to think about it is probably, without getting into the mathematics, the answer would be that when you're trying to understand what transformation works, typically you can have a very because it's always numbers going into numbers, right? You always start with numbers. Pixel values, if it's like an image, every kind of data that you have inside a computer, which is like a piece of text, like a news article, an image, an audio sample, everything is going to be written as numbers. It's going to be stored as numbers. That's all the computer can understand. So, because it's always going from one set of numbers to another set of numbers, there's always some kind of complicated calculation which relates the two. Just like you can say that 4 and 6 are related by the +2 function. You can add 2 to 4 and you get 6. There's always some kind of calculation which connects the two. It's mostly approximating this complicated calculation is what we use deep learning for. That's the standard use.
And one function of that is to get.
Yeah, exactly. And it's used across the board in terms of applications as well. People use it in protein DNA interaction and understanding. People use it in chemistry, in manufacturing, in finance, everywhere.
Conscious type of, but as it was brought up that IBM said that because certain jobs don't require someone that have all the knowledge or all the general jobs will only require a certain skill set. That how far do you think we are from, say, AI being viably competitive?
Well, you know what? When calculators came out, that's the conventional answer people who believe in AI. So when calculators came out, they put people out of jobs. Originally, when the whole war effort and stuff were going on, people used to sit down and calculate numbers by hand, right? There were slide rules. I've never used one, but I've seen people use one. A slide rule is like a calculator where you can calculate, like do addition and subtraction and things like that. And then calculators came out, and you needed lesser number of people to do those same calculations. So people got replaced there as well. The idea is that any kind of new technology does create a change in the job patterns, right? So it's quite the big question that people are discussing is if the change in the job patterns that AI is going to bring is similar to like the ones you've seen before, where some jobs were lost, new jobs were created, people by and large found a new job for the most part. If it's the same, then it's okay, doesn't matter, right? The big question is if it's so radically different that a huge chunk of people are going to be put out of job and they can't find a new job. So the technologies that we see right now, I don't think so. But once again, monetization and jobs are things that are so complicated and best left to economists. But I don't see this replacing a person at any task anytime soon from the perspective of how powerful it is. And to clarify just the IBM thing that you were talking about, I think the news says it talks about compute power. What that means is that how powerful is this computer? It's not exactly talking about the kind of tasks it can do. It's talking more about the number of tasks it can do. How fast can it run calculations for the most part? So whenever they say by this year the compute power will be at par to this much, trying to say they're as powerful as they can do as many calculations as X. That's the idea.
Great. Cool. If you have more questions, come up afterwards. And also, if you haven't taken some time, take a minute before you leave and fill out the survey. Let us know how we're doing. Yeah, let's give Spandan another hand.